So we're going to briefly review thermodynamics, and then we're going to get into kinetics. So when we talk about thermodynamics, we know that we always talk about it in terms of the system and in terms of their surroundings. So when we're talking about our system, we can have an open system, a closed system, or an isolated system. An open system is going to let out both matter and energy. Okay, an example would be a coffee cup, right? All your water vapor or steam can come out the top, and your energy can go out the top and out the sides. Another example could be a campfire, right? We can think of when we're categorizing our systems as the containers that hold what we're looking at, right? Your closed system is going to let out energy, but not any matter. Okay? Example of a closed system would be a pot with a lid. Okay? A pot with a lid on the stove, or a water bottle, right? Your water can still get warm, right? If you have cold water in a water bottle, it can still get warm, but it's not going to spill. And then an isolated system doesn't let out water or doesn't let out energy or matter. Okay, and our only true isolated system is the universe, right? Because no matter where the energy goes, if it gets transferred from one thing to the other, no matter where the energy goes, it's always going to be contained within the universe. But our best knowledge is a cooler or a Yeti thermos, right? The Yetis are the best. They're common, but any type of thermos really can be considered an isolated system. We've also talked about our calorimeter. We treat our calorimeters as isolated systems. Number 4, thermodynamics. We already said this. It's always described in terms of a system and its surroundings. Okay, thermodynamics, we always talk about it in terms of the system and the surroundings. In an endothermic reaction, we know that heat is absorbed from the environment into the system, and an exothermic reaction, energy is released by the reaction into the environment or into the system, or by the system into the surroundings. So when we talk exothermic and endothermic, we have to first label our axes. Exothermic reactions, or chemical reactions in general, always take place over time. So we have our time axis on the bottom, right? Both chemical reactions always take place over time. And on our y-axis, we're trying to figure out what is happening to the heat or to the energy as the reaction proceeds. And we know that our units, our heat or energy, are in joules. So we have heat or energy in joules. Okay, so an exothermic reaction, whenever we start a chemical reaction, we start with our reactants, right? Our reactants. And because it's exothermic, again, exothermic is losing or releasing energy, so our products are going to end up with lower energy. Products are going to end up with lower energy than our reactants. And to connect the two, we get a bump, jump, and connect. Okay, so for example, if our reactants are A plus B, and our products are AB, we know that we have some amount of energy in our reactants. This little section from here up is called our activation energy. Okay, that EA, it's called activation energy. So over here in the corner, EA, is your activation energy. That's the energy needed to start a reaction. Okay, your activation energy is the amount of energy needed to start a chemical reaction. So when these reactants are running around bumping into each other, right, they bump into each other, that's why they have some starting amount of energy. They're bumping into each other. If they bump into each other in the right way and with the right amount of energy, they increase and then they create your products. Okay, so here we have our activation energy, and then here from the line of the reactants to products, we're going down because we're losing energy. This is your delta H, right? This is the amount of energy that we've lost over the course of this reaction. We can do the exact same thing for endothermic. Endothermic, your reactants start at some amount of energy, right? If we were to look at this chemical reaction, it would be A plus B makes AB, and it's thermochemical. Your delta H, we've lost energy, is some negative number, right? That's your thermochemical equation. So for an endothermic reaction, you have your reactants again. Your products, it's endothermic, so we're absorbing energy. Right? Endothermic is absorbed energy. So your products are going to have a higher energy than your reactants. And same thing, we need our activation energy barrier, so we have a boop jump and we come back and meet up. Notice that your reactants and your products are a flat line. Energy is constant until the reaction starts. Okay, so for this one we can have AB reacts to make A plus B. Okay, so our reaction here, AB breaks into A plus B, and our delta H is going to be a positive number. And we know that because if we draw our line across, we have from the reactants to the products, this is our delta H. We're going up from reactants to products, so it's energy gained. And then our activation energy is always from reactants to the top of that bump. So this reaction takes more energy to make products than this reaction does. Okay, AB makes A plus B, delta H is positive. Okay, if we look at this is our little reaction beaker. So if we pretend that in this one our reactants are a bunch of A, and we've added to it a bunch of reactant B. When those two things react, they're going to release energy, so your heat goes out, and it's going to feel hot to the touch. If this is your reaction beaker and you have AB and it's trying to break down, it's endothermic, it's absorbing energy, which means your heat is going to go in and it's going to actually feel cold to the touch. So if you touch this, it's going to draw heat from your finger into the system, and your finger is going to feel cold. Okay? We should all know conservation of energy is that energy can't be created or destroyed. It can only be transferred from one type to the next, or from one type to another. Can't be created or destroyed. Can only transferred. I can't spell today. They're going to say converted from one form to another. So that means from kinetic to potential, from electrical to chemical, from chemical to kinetic, so on and so forth. Okay, so that's our little review about thermodynamics. Now we're going to go ahead and start reaction rates. So reaction rates can be affected by a bunch of things. Reaction rates is a fancy way of saying kinetics. Okay, reaction rates is a fancy way of saying kinetics. Reaction rates, if you want to make a reaction go faster, you can change the temperature, right? If it wants to go faster, you can heat it up. You can change the concentration of your reactants. Okay, that's a fancy way of saying how much we have. You can change the surface area. Of your reactants, or you can change the reaction rate by the presence or absence of a catalyst. Okay, whether or not you have a catalyst will change your reaction rate. And remember, rate is just how fast. Other factors that can affect reaction rates, if you have the actual nature of the reaction, the type of chemical reactants you have. So ionic compounds are actually going to react faster than covalent ones. That's because your ionic compounds want to donate or receive electrons completely. Let's say covalent compounds, they have to decide whether or not they want to share. Is a good way to think about it. Your increased number of chemical bonds is going to actually slow down your reaction rate as well. So if you have a single bond versus a double bond in your covalent chemicals, that's going to affect your reaction rate. And then pressure. Pressure is for gases only, and that's hugely important to remember because we know that liquids and solids are not compressible. So changing the pressure isn't going to affect the rate of a reaction for a liquid or for a solid. Solids and liquids are not compressible. Yeah. So increased pressure is going to increase the reaction rate for gas only. And remember, when you increase the pressure, increased pressure means you're increasing the collisions with the walls of the container and with the other gas molecules. And it's those collisions that actually cause a reaction to happen. So if we look more in depth at temperature, if you increase the temperature of a reaction, your molecules are going to move faster, right? We know this. We know that this is called kinetic molecular theory. We know that this is called kinetic molecular theory. Kinetic molecular theory says that if you increase temperature of the reaction, you're increasing the kinetic energy, which means your molecules are moving faster. Okay, the faster that molecules move, the more they are going to collide with one another, and those collisions means the reaction will happen faster. Okay, so collisions means reaction. Reactions are caused by collisions of molecules. If we turn it over, head to the back, We look at the next thing is concentration. Increased concentration is also going to increase something called the collision frequency. Collision frequency is just a fancy way of saying the more often that molecules collide, the faster the reaction is going to happen. So frequently is how often the reactions or the reactants hit each other. We're going to look at low, medium, and high concentration of reactants, and we're going to draw it with hydrochloric acid or HCl. So HCl, remember that AQ means it starts with H, ends in AQ. It's an acid. Hydrochloric acid. Okay, hydrochloric acid is what we call a strong acid, which means it dissociates in water. Okay, strong acids, they dissociate in water or they break apart. Dissociates is just saying they break apart in water. Okay, so if we look at a low concentration, I'm going to put this in the margins. Concentration is usually abbreviated by these brackets. Okay, concentration of reactants, it's abbreviated by brackets, and it's measured in molarity. Okay, so moles per liter of solution. Concentration is measured, usually represented in brackets, and it's measured in moles per liter of solution. So it's some amount of chemical in 1 liter of solution. Okay, it's some amount of chemical in 1 liter of solution. So if we have a low molarity or low concentration solution, we have 0.1 molar. This is all relative, just to give you an idea of what a low molarity versus high molarity concentration would be. So it's all very relative, but 0.1 is usually pretty low concentration. So we don't have a whole lot. We're drawing hydrochloric acid. It breaks apart in water, so we have H+, and we have Cl-. HCl combines in a 1-to-1 ratio, so for every 1 hydrogen ion we have in solution, we also have 1 chloride ion. So we're going to draw a pretty low molarity concentration solution of HCl. If we have a medium concentration solution, we're going to have a little bit more hydrogen and a little bit more chlorine. So here we drew 3, oops, one more. We've got a little bit higher concentration. So 1 molar is usually a medium concentration solution. And then at high molarity, try and get all of our volumes the same. At a high molarity solution, we have lots of H+ and lots of Cl-. Because high concentration means that you have a lot of things in solution. Right? And if you look, which one of these is going to have more collisions, right? Collisions means reaction rate. More collisions means faster reaction. A higher concentration is going to have more collisions, which means it's going to have a faster reaction rate. Okay, that capital M, that stands for molarity. Okay, and that molarity is your concentration, moles per 1 liter. Okay. The next thing that can affect your reaction rates is your surface area. Okay, surface area is a physical property of solids. Okay, only solids have any surface area. Liquids and gases both take the shape of their container, so they don't actually have a surface area. If you have a 1 centimeter sugar cube, let's see if I can. Yep. 1 centimeter sugar cube. 1 centimeter on each side. Then your surface area is going to be 6 centimeters squared. 1 centimeter for each face. If you have the more surface area you have, the reaction is going to happen faster, because each face of the cube that's exposed to the reaction, that's the place where the reaction can happen. The reaction can't happen inside the cube. It can only happen at the surface. Okay, so the more surface area you have, the faster the reaction is going to happen. Okay, more surface area increases the frequency of collisions. And it's important to note that smaller pieces means you have more surface area, right? If you think about something dissolving, is its sugar cube going to dissolve faster, or is granulated sugar going to dissolve faster? So smaller pieces, like the granulated sugar, is going to actually dissolve faster. The reaction rate is going to be faster. Okay, if we think about it here in 2 dimensions, here you have this cube, the reaction can happen here at the surface. So your surface area is equal to one, right? You have 1 centimeter by 1 centimeter by 1 centimeter by 1 centimeter. So the reaction can happen, right? If this is coming off the paper, and let's say your chemicals are here, like hanging out around the outside. Okay, they're just hanging out, not at the surface, but let's say they're hanging out around the outside. Boop, 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 boop. Right, so every time one of these little circles collides with the surface, a chemical reaction happens. Collision here, collision here. Okay. Your reaction can happen at 4 different surfaces, so your surface area is 4 centimeters squared. If we break this apart into a little bit smaller, now you have 0.5, 0.5, 0.5, right? We've broken each piece into half. So you have the same surface area around the outside. Boop, boop, boop. Let me change the... Right, you have the same surface area around the outside for reactions to happen. But now, because we've broken this, we also have reactions can happen in here. So not only are collisions happening out here around the outside, they're also happening in here at this additional surface area. So we've added an additional surface area. So now we have 2, right? 0.5 plus 0.5 plus 0.5 plus 0.5, right? We're adding around the perimeter because this is where our reactions are actually happening. So we've added 2 plus 2 plus 2 plus 2, which is surface area of 8 centimeters squared. And if we imagine that we break it up even smaller, now we have 0.25 for each cube, and each cube has 4 sides. So 0.25 plus 0.25 plus 0.25 plus 0.25, we have 1 centimeter squared on each, right, reaction potential place where the reaction can happen. All the way around the outside, all the way in here, and all the way in here. So now our surface area becomes 16 centimeters squared. Okay, because the reaction can happen inside and all around the surface of each section. Okay, so if you grind things up, let's see, if you have a powder or ground chemicals, these will react faster. Okay, so there's a little note. Powdered or ground chemicals will react faster. Okay, last thing I want to talk about is the addition of a catalyst. A catalyst is a substance that provides an alternative or lower energy pathway for a reaction that increases the speed of a reaction. A catalyst is not used up. Okay, it's not used up during the course of a reaction, so it's going to be the same in the reactants and in the products. Okay, so a catalyst, what a catalyst does is it lowers the activation energy. It lowers the activation energy of a reaction. Okay, so we know that hydrogen peroxide decomposes. The decomposition reaction. So we have H2O2. It decomposes into H2O liquid and oxygen, O2 gas. So if we have 2 of these, we have to balance the reaction first. When we add a catalyst, it goes a lot faster. So you'll see in lab, if we add yeast as a catalyst, it's going to cause the reaction to go even faster. Okay, hydrogen peroxide, that's why it bubbles. The dirt, if you have dirt in a cut and you put hydrogen peroxide on it, it bubbles really fast. That dirt acts as a catalyst. Okay, so we're going to draw an energy diagram for an exothermic reaction with and without a catalyst. So our energy diagram, we know, has an axis of time. On the Y, we have heat or energy. It's an exothermic reaction, so we have our reactants. Exothermic means it's going to release energy, so our products are going to be lower. And we have jump activation energy that causes our thermochemical change. With our catalyst, we said that a catalyst lowers the activation energy. So we're going to have the same reactants. We're going to have a smaller jump, and we're going to have the same level for our reactants. So we've only changed the activation energy. Okay, so the pink is with a catalyst, and the purple is without